So if you have a big impact, either into the ice sheet or into the ocean, that the impact vapor plume isn't going to go up just 58 kilometers, because the height to which the plume rises is basically a function of the amount of heat that's injected. So the more heat, and water has a tremendously higher heat capacity than air. So if you vaporize water, you're getting stuff that's going to go to the top of the atmosphere and into space. So I think that these microparticles from the Younger Dryas could be all over the planet.
Hello, I'm Randall Carlson, and I'm here with Dallas Abbott, and we're going to have a very interesting discussion, I'm convinced, about a lot of the things that she's been studying and researching for decades now. So this is another episode of Squaring the Circle podcast, where I talk to some of my favorite and most interesting people that I can think of. And so I think we're going to fulfill that criteria this evening. So hello, Dallas, and thank you for agreeing to do this conversation with me.
Well, thank you. I'm delighted to be here.
Yes, and we were having a little bit of discussion here before we started the recording, and we were talking about a paper when you first published a paper, I believe, at a conference. At least you gave a talk about Burckle Crater, and you said that was in 2020. And I'm thinking now, gosh, that must have been about the time when I first heard about your work and started following and reading your stuff. But I guess it was that long ago.
It was, no, it was longer than, it was 25 years ago. It was Atlantis 2000.
Yeah. That's what I'm thinking. I mean, it was, so was there a paper published? Did you publish a paper at that time?
Yes, I published a paper with Bruce Massey.
Yes.
And he's an anthropologist, archaeologist, who had been compiling flood legends. And what he was working on was trying to find accounts where that first of all, the what was recorded had not been, people weren't just repeating what was in the Bible.
Right.
It had not been influenced by missionaries, and also where aspects of the stories, and I should say oral histories, where there were clearly elements that were not in the biblical flood story.
Right.
And there were several elements that were suggestive of impacts. One was where people recorded hot water from the sky, and another, and I mean, they're talking about boiling water from the sky, which is something that you would get if you had a big oceanic impact.
An oceanic impact, yeah.
Because the temperature of impacts is estimated to be like at 15,000 degrees centigrade, certainly well over the boiling point of water. Mm-hmm. So you would vaporize a lot of seawater. And then that seawater would travel, a long distance before it condensed again and came down. It just, the distance would depend on the size of the event. And the other thing that Bruce saw was there were oral histories where they saw like flaming objects in the sky on ballistic trajectories, which sounded like fragments of the impact ejecta that were coming down they were coming through the sky, and they saw this before the flood storm, which makes sense.
Right. The ejecta would arrive first.
They
obviously.
Would. And
let's define, just so people listening, ejecta would be when the object, the bolide, strikes, assuming it strikes the ground or strikes the ocean, it's gonna eject enormous volumes of material into the air. And in the case of an ocean, what you're saying then is that the water will go up as vapor, and then it'll be carried by wind currents, presumably, many hundreds, maybe even thousands of miles from the point of impact. And then the secondary, if there's actually, like in the ground, or if it penetrates the water column and strikes the bottom of the ocean, Then there would be ejecta, solid material that's the ejecta, and that falling back to the earth could cause secondary fires, right?
That's
And
exactly right. So
now that I'm using them, I'm finding out that they're really a super tool for somebody like me who likes to research and likes to keep up with what's going on in the world. I made the point earlier in a discussion about it that I was looking for a substitute for reading my morning newspaper every day. So I just wanted to show you a couple of things that I really particularly like about it. First thing is I've set up, for you. So I've picked some topical matters, and whenever there's stories about these topics that have a particular relevance or interest to me, all I got to do is click right here and I get this menu right here. And here's all kinds of cool stuff. Here's something, of course, that I'm going to be all over this. Newly discovered bus-sized asteroid will zoom close past Earth tomorrow. So then I want to know more. I just click, and here's my story. And look I've got all these different perspectives on this story. Over here, if I want to get more specific, I can go up here to the search bar, and let's say I want to put in, asteroids. Let's see what happens if I put in asteroids. And look at all of this that comes up. China sets up planetary defense unit. NASA monitors 5 aircraft-sized asteroids after exceptionally close. So look at this. So it goes. See here, I got a bunch of topical articles and research publications about asteroids. So I was never able to do this with the old morning newspaper over breakfast. I can tell you, did not have this functionality. Right now, you can get a 40% off their Vantage plan for just $5 a month. Click the link below to subscribe to groundnews.com/TRC. I hope you'll equip yourself with the powerful tool of Ground News just like I have. And in doing so, support our work here at Squaring the Circle.
you would have ejecta, because if it's 15,000 degrees centigrade, that you're going to melt the rock.
It's molten.
You've got molten ejecta of all kinds of bits and pieces of the area beneath where you form a crater, and a small amount of material that's also the impacting object. Most of it's going to be terrestrial material, but it's going to be terrestrial material with a difference. A lot of it would melt and turn into glass, for example.
And this would also account for the formation of tektites, correct?
Yes,
And tektites could have a mixture of both the target material and the impactor itself.
That's right. The thing about tektites is you only get them in a special case. When an impactor comes, the average angle that an impactor comes in is 45 degrees. And to get tektites, you need to have something that's coming in at a low angle, probably less than about 20. And then what happens is the tektites are downrange. They're on the opposite side of the crater from the side that the impactor entered.
Okay, so I didn't know that fact about that low oblique angle as being a major factor in the formation of tektites. I didn't know that, but so I've learned something here that's going to be.
Yeah,
I
and also, of
now.
course, this tektites are extremely glassy, so you have to have a substrate that's got the right composition to melt to form a silicate glass. In theory, you could have a substrate that didn't have the right composition, and it would melt, and you wouldn't have something that was preserved. But from there's quite a few impact events where there are tektites.
Yeah, there was the Potomac Bay. What's it called? The crater.
The Chesapeake Bay
crater created a tektite field, and a lot of those are found in Georgia. There's the fall line down near Macon, where I guess somewhere near that Eocene. I think it was Eocene, around 35
It's Eocene.
million years
It's
ago.
80 million years roughly.
80 million.
Yes.
It's Eocene. Yeah. Okay. So that when it hit, the splash came down over Georgia, and there's a outcropping of that strata. I forget what it's called, but if you go down there after heavy rain, oftentimes people will go down and it'll wash out tektites that are from the Chesapeake Bay impact.
No, it's not. It's sorry. It is Eocene, but 80 isn't right. But anyways, I think
I
it's
think
80
it's
million years, but that doesn't fit because the KT boundary is 65. So, anyways, it's old.
it's old. It's older than you or I put
Yeah.
together. So, although maybe not for too much longer. Okay, so they've got a whole exhibit, or they used to, at the Fernbank Science Center, which is in DeKalb County. It's mainly for the DeKalb County school system, but it's a nice science center, and they have a nice science library there. That I used to haunt that library for several decades until the internet kind of took over, and I was able to get most of what I wanted online. But they have a nice collection of the Georgia Tektites there at that science center, or they did for many years, and they were from the Chesapeake Bay impact. So,
Yeah,
but
the Chesapeake Bay crater is Eocene, Upper
yeah,
Eocene.
Upper
But
Eocene, which puts it, so I may have been in the right ballpark then.
yeah,
There,
no, it's Eocene. I just
yeah,
looked it up, but
okay,
but the number, the age that I said wasn't quite right.
okay. Well, anyways, okay, so you've been doing this work and discovering these tsunamis, and I was particularly impressed with those tsunamis that struck southern Madagascar, which presumably emanated from the point of impact that produced Burckle Crater.
Yeah, I believe so. I've modeled it, and it could have been the source.
We,
And it's in the right direction because one of the things I learned from Slava is that you basically the direction the length of the chevrons, the back azimuth
back azimuth, yeah.
points
Will point
towards the source, and Burkle is in the right direction, and
but we need a
it also the right
submersible
size.
and the right size,
Yeah,
because I'm not sure how to pronounce the names. Ampalaza, is that
Ampalaza,
Ampalaza? Is that even?
Fenambus. I learned how to pronounce them from the Malagasy scientist. I didn't know either.
And how does he say it, or he or she? Ampa what?
Well, Ampalaza
Ampalaza. Okay,
and
Ampalaza.
Fenambus.
Fenambus, and
Yeah, yeah,
Ampalaza. Let's see. So
that's what they said.
Fenambus was the one that washed up over the escarpment. Am I right? Or is it the other way around?
Oh,
There was
I think
it draped over that escarpment, and the escarpment, I think, was a couple 100 feet at least above the coastal plain at the bottom of it.
yeah.
And you have in this paper, you
The
have
Ampalaza is no the Ampalaza goes up to 63 meters above sea level, and Fenambus goes up to 186 meters above sea level. So
that was the one.
that's the
That was
one that went up the escarpment.
right. That was the Fenambus.
Right.
And I got that right? Okay.
Yeah.
So by the fact that it went over that escarpment tells you that the wave, obviously, that almost in a sense provides a minimum height, right?
That's right. Basically, the minimum, you have two things in a tsunami. You have what's called the run up, which is the height above sea level that the
Yep.
wave travels, and basically the actual wave height when it was traveling through the ocean is about a third that. But I mean, you're talking here, if it went 186 meters above sea level, you're talking about a wave that was, 60 some meters high. It was
Yeah.
really high.
So that would cause a lot of damage on any coastline if such an event were to recur today, especially
Yeah,
along a populated coastline. It would be a disaster of incredible proportions.
right. Because the other thing is the thing went like it went tens of kilometers inland.
and that is called the run in.
The run, well, the run up is the height above sea level. I don't know what they call the distance inland it goes. Run in
I've
is
seen
about
it
as good
referred
as
to as
any.
the run in distance, the run
Okay,
up height and the run in distance. And I've explained to people that obviously the steeper the grade of the coastline, the shorter the run in distance. If and because we were discussing tsunamis during the late glacial maximum, and I pointed out that, well, with a 400-foot whatever lower sea level, a lot of the shallow gradient coastal plains would be exposed. And if you had a tsunami event during late glacial maximum times, your run-in distance could be considerable because
you're right.
you're just going over this low gradient coastal plain until you get to the continental mainland.
That's right. I mean, the Fenambus, it went, it's 45 kilometers long. The other
Yeah.
one, the Ampalaza, is also, it's the same. It's 46 kilometers long. They're both pretty similar in terms of their run in.
Maybe it would be interesting for people if I did a share screen. I could do a share screen here. I've got Google Earth is open, and we could look at those and you could talk about it. Let's see if that'll work. I'm going to go here. I'll share
Yeah,
my
I think
screen.
the images I have were among the best. I don't know if the current images on Google Earth are as good.
Well, if you think that yours are better, we can just switch over. Let's see here. That should be it. Okay, we're at the southern sector of
Yeah,
Madagascar here.
one of the reasons that Madagascar, yeah, there you go.
Here we go. This is the Ampalaza, right?
That's right.
Yeah, and yeah, you can see. Now, let me see if I'm understanding what we're looking at here. Because basically what we got to understand here is these deposits are going to show this bimodal character of the flow because it flows in one direction and then it flows back out.
That's right.
So this flowing, this return of the water to the ocean, if this is, because typically would think you've got a single direction, this would be more almost like a current field, field with parallel to subparallel ripples, right? And then if that's the first iteration, the water flowing in, then the water flowing back out is essentially what creates these the chevron shapes. Is my understanding of that sound
That sounds right. That
feasible?
it's the water that's flowing back out.
Right.
Because I mean, if you see even a wave on a beach, you can see that some part of the wave will go a little bit further along the beach. I mean, up the beach, and then as it flows back out, you'll get some kind of shape in the sand that looks somewhat similar to the chevrons, but on a much smaller scale.
So here, I mean, you can see so distinctly here actually where the wave came in, washed in, and then deposited. And of course, we should also mention that as the wave is moving inland, it's also losing energy. And as it's
That's
losing
right.
energy, it's losing its competency to entrain sediment. So it starts, and this is why I would think now, if I'm thinking, my thinking is not correct here, correct me, but we're finding these sand deposits here because that will be the finest grade sediment that it's carrying up to its distal reach of its inland flow. And then
Yeah, but these sand deposits, the thing is they're not like windblown sand. They actually entrain coarser particles in them because of the energy of the wave. And so
and they're
they have benthic marine microfossils in them, and those things are too big to be carried by the
by
wind.
wind. And I'll mention for listeners, benthic marine fossils. Those come from creatures that are living on the bottom on the sea floor, basically.
Right. So they
And that,
probably came from the shelf
yeah,
nearby.
that would seem to make sense. And then something else I wanted to ask you about. So if we can picture what's happening, the wave is washing in, slowing down, and here it reaches this is its distal reach. It's pretty much at this point where the water flow, the current flow, reverses direction to flow back out. It dumps this sand here. Now, this sand, would you think that this is a separate event, or could there be a secondary wave of less magnitude that comes in and then
Well,
dumps this? What?
no, I think what's happening there is that some of it's getting reworked by the wind. That the
Okay, so
primary structures that you're seeing are the things that are mostly sediment covered, the parts that are sort of green and brown.
yeah, yeah,
So,
all the
so, so then what happens is you've got a lot of sand, and if you happen to have winds, and we were down on the coast there, and it was quite windy,
okay,
and so I think some of those I don't know their age. I mean, some of them look like they have the right outlines to be chevrons, but wherever it's all kind of white. It's getting in part it's getting reworked by the wind.
okay. So, which totally makes sense. But my thought was maybe there was an initial deposition by water, by a wave, and then has been reworked by wind ever since.
That's
I guess
right.
I just got to go there and take samples and figure it out, right? So,
Yeah, well, that's
um,
what we did. We went there and we took samples, and what we
and
found was that the components of the chevrons could not have been entirely windblown.
not entirely right.
No, I
So,
mean
so you could,
because they contain too much coarse material, and they contained marine microfossils that could not have been moved by the wind. And one reason why marine microfossils, they're two, what we see on the fossils is pretty interesting. Like one side will be kind of pitted, and the way that the
hmm
sand moves, it's a process called saltation.
hmm
And so the grains, when they're being moved by the wind, they jump.
yeah,
And so what you can see with these marine microfossils very often, the really big ones, is that one side you can see looks nice and you can see the features of the shell, and the other side is all pitted. And I think what happened was it gets moved in by the tsunami and it just sits there, but then the things are moving around it and the sand grains are saltating over it, and they're making holes in it basically.
okay,
And the other thing about it is that the reason why sand, survives, why you get all the sand in deserts, is because quartz, which is what sand is made of most of the time, or this sand certainly, if you if you take it and you move it with the wind, what happens is you round the edges off, but it
yeah,
doesn't break up. It just stays. All that happens is the grains get rounder and rounder, but the microfossils are made of the mineral called calcite. And if you
hmm
take that mineral and you hit it and you break it, it'll break up into little tiny cubes. And so it'll
hmm
basically just kind of disappear.
aha. And so that's kind of a marker that indicates to you then. Um,
Yeah. And so if you have these bottom living foraminifera, the benthic foraminifera,
mhm.
that can't be moved by the wind, and they're still preserved, the only way that they could have gotten there would be with something like
Right,
a tsunami.
right. So then now we're down here by the, make sure I get this pronunciation,
Yeah,
Fenambazi?
here's it.
How did you, that's what
Fenambus.
this one is, right?
Yeah,
This is,
Fenambus. And that
we were
one,
looking at the
that was the one when Google
Ampalaza
Earth came out
up
and I
here.
saw it. I
I got
was,
to
I
get the
was,
names correct.
now I'm losing
Let's see.
connection. Okay, yeah, when I
Fenambozi,
saw that on Google
right.
Earth,
Okay,
I
so here,
immediately knew I wanted to go there.
I'm sure you did because I did the same thing. I want to go here. So here, let's point out. So here's the escarpment, which I believe was
That's right.
a couple of 100 feet high,
It's
and you
175
can see
meters
it
high.
175 meters. Okay, so yeah, that's for people in America that are used to the imperial method. You said 135 meters. Trying to think.
175.
Oh,
So
100,
it's
yeah,
it's
175. So if you think in feet, that's 574 feet. But the base of that escarpment is already above sea level by how much? Well, we could tell here. Let's see. If I
It's not
set
very
my
much above
cursor
sea
here.
level.
Well, it says it's
I'm saying
right
at
here
the
where my
top of the
cursor is.
escarpment, the
It says,
175 meters above sea level.
yeah. So, 231. I've got it set for feet. So we're at 230 feet already above sea level here. So we would add that essentially. Yeah, I mean, so up here at top, it's showing that I'm 500 feet. 500 feet. What does that turn into meters? 502 feet. It says the elevation up here at the top where my cursor is. So if we go follow this to the northwest, the escarpment is very plain to see, but then look what's happening right here. And notice that the distinctiveness of the escarpment is suddenly obscured. So what's happening there, Dallas?
So what's happening is that the tsunami wave is traveling up the escarpment and depositing material on top of the cliff.
On top of the cliff.
That's
Right.
right.
So then that tells us that the wave had to be high enough to overtop the cliff
That's right. And you can
when
see
it made
that
landfall.
that's right. And you can see that the sand layer is thicker below at the bottom of the cliff than it is the top, but you can still see that some of the sand made it up there.
Yes, yes. And the outline of the wave deposit is very distinct. I mean, it's easy to see. We're following it around here. You can actually follow it up to here till here's its terminus right here. And
That's
then
right.
it looked like, yeah. So now the next question is, early on in some of the early stuff, you were estimating maybe 4 to 5,000 years.
Oh, no, I
Where are
think
we at now
this is
with the
Younger
dating?
Dryas. We
This is
dated,
now young. Okay,
this
no
is
kidding.
like, this is Younger Dryas age. Bruce Massey had another estimate, but I did carbon-14 dated there were enough marine microfossils in the Chevron that I could basically, what I did was there were also land snails. So I picked out all the land snails, and then the carbonate that was left was the marine microfossils. And I just took a whole bunch of sand, estimated its average carbonate content, and sent it off to be dated.
And it came back Younger Dryas.
Yep, it came back roughly Younger
Well,
Dryas,
that
like 13,000 years ago, roughly, 12, 13,000.
yeah. So that to me really raises some interesting questions. So this would probably have been one impact of a multi-impact event.
That's right.
Is
I
that?
mean, there's evidence for, impact events all over North America. But
Yeah, yeah.
but from the oral traditions that Bruce looked at, they were centered around the Indian Ocean.
Yeah. Which would right. So well, yeah. So I'm still trying to wrap my head around if we were in a spaceship hovering safely out in orbit somewhere watching what was unfolding on Earth during the
Okay, well,
lower
there's
Younger
also
Dryas.
chevrons in Australia, although they haven't been dated as quite as old, but I I think they could be from the same event. And there are also
Uh-huh.
chevron deposits in India. So they're basically, and they all point, the back azimuths all point back to Burkle.
Mm-hmm. Mm-hmm.
So, and the Australians, there's a paper by Anya Sheffers where and Dieter Kelletot where they estimated the source of the chevrons in southwestern Australia, and they
Uh-huh.
estimated its latitude, and the latitude is the same as the latitude of Burkle. So
No.
they
Okay.
estimated the source at the same latitude as Burkle. They didn't estimate. They said either the source was a sediment slide or an impact, and they couldn't. Of course, they couldn't tell. And so it's further
Yeah. I
west.
further
You gotta
west this
go
way.
right to the coast there. Yeah, I don't know how well this
I've
shows up on Google
I've
Earth. I had
found
a
them. Once you
map,
find them, they're pretty prominent.
right.
It's
I had a
been
map.
a while.
It's it's
Yeah,
southern. It's not that far north. It's southern.
I'm too far north. Okay,
Yeah, it's southern Australia, and those
okay,
things go up to about 150 meters above sea level. Now you're getting too far, but the map of
too
Dieter
far. Yeah,
and Sheffers is better at delineating them. I don't think you can see them really
yeah.
well on Google Earth, probably because too
No,
many
they're
people
not. Sure.
are at the coast.
Okay. All right. So it's very possible, if not probable, that the chevrons that are on the coast of Australia are from the same impact event. And Burkle, let's see, it's going to be down in this area somewhere.
Yeah, it's like 20 south. It's east of the ridge. Yeah,
And
this
this
is
is
the
this the
southeastern
ridge?
ridge, so it's east of the ridge. Um, yeah, so in that
Could
area,
that be
but
it?
on pretty young. Well, you can't really see it on that map. I have
Okay, yeah,
a seismic
a better
cross
map.
section and a map, a local map, but it's only it's only like 14 kilometers wide or so. But because of the water depth, it forming a crater. I mean, that's the size of the crater in the crust. The size of the crater
Right,
in the water would have been much
water,
larger.
much larger. Right.
So,
So,
so
just
you can't really see it very well. But I have a seismic line where I can see something, a disturbance of the basement in a flat sediment pond. So that's
okay.
where
So,
we've definitely found some things that look like, impact ejecta, up,
and
up on the ridge crest. It's not exactly at that location, it's further north. But remember, the
okay,
tsunami wave, when it starts out, it's going to have tremendous energy. And you need to get to a location where it
right.
slows down enough to deposit material.
Right. And what happened when that wave hit southern Madagascar is it sort of refracted or wrapped around the southern coastline.
Right. And
If I
one
got the
reason
picture
why
right?
That's right. And one reason, notice that the continental shelf, you can see it there in the picture, in the
Mm-hmm.
area where the chevrons are so
Yeah.
prominent, the continental shelf is quite, the edge of the shelf is quite steep and narrow.
Mm-hmm. Yeah.
So that helps you in
Yeah.
terms of,
And this
yeah. So
and this
the
is we're
continental
seeing
shelf is
tsunami
not the,
deposits right here. Yeah.
yeah. So
Right. So like you said, the back azimuth going back this way, it's almost you can take the axis of the chevrons. Going forward, that would be your azimuth, and then reversing would be your back azimuth, and then
that's
that would
right.
be directly pointing to the energy source,
That's
whether it's
right.
an earthquake, a slide, or an impact. That's going to give you a pretty reasonable, accurate location for the impact or whatever the event is that's triggering the tsunami. So Younger Dryas, I'm going to have to process that because I just somehow I missed that detail
Well,
until I think I read.
in the
Let's see,
article in the New York Times, Bruce had estimated it was only about 3,000 years
that's
old.
where I
But
got the younger date from. I guess
yeah,
is from
but
Massey's work.
but
Yeah.
but when we dated it, it turned out to be older than that.
So then the impact, the Younger Dryas, and we're talking about 13,000, give or take a few centuries. We're talking about the lower Younger Dryas boundary.
Yeah, the
We're
start
talking
of the
about
Younger Dryas.
the beginning of it. So we're talking about some kind of an impact event, which seems to more and more. I'm going to stop sharing for a moment. More and more seems to be a multi-impact event.
Oh
I
yeah.
mean, we're taking a little bit of a detour here to tell a story that I think is going to be valuable. I was coming down the stairs, and I think somebody just ahead of me had spilled a little bit. My foot hit it, slid out from under me, and I tumbled down 3 or 4 stairs to the bottom. I sure banged up my left knee. It was painful, but I was very relieved to remember that I happened to pack my CBD from the gods salve. And I was really grateful that I had remembered to do that. So that night I put some of the salve on, went to bed. Though I've being in the construction and building industry, I've had many falls and injuries and stuff, and I figured I'm going to be laid up with this for a month. We drove home. I think it was 3 to 4 days later. I continued applying the salve, and I would say within a week I was getting around pretty good. I always bring the oil when I travel, and I'm now, after this episode, I'm like, okay, I'm always going to have the salve with me too.
I mean, because the stuff that's all over North America could not have come from an impact into the Indian Ocean. I
Correct.
don't I
So
don't think.
right. Well, this is why I've kind of thought for years that there, was probably an impact over the northern hemisphere, and at least some of it uh, impacted the ice sheet. And let's see, I'm down here in the
Yeah,
southern
I mean, one of
hemisphere.
the things that I think people should look for is if you have a big impact that hit the ice sheet, I think it's going to trigger multiple sediment slides on the margin, much like this Storega slide,
Burgess slide. Yeah, yeah.
and you'll get, and so there'll be tsunami deposits of the same age, and it is possible to date the sediment slides at the base of the slope.
Okay, okay, that makes
I mean,
sense.
so you should see those features. And the one that was talking about in the Hudson Canyon is younger. It's only about 3,000 years ago. It's not Younger Dryas,
And
but people have have found deposits at the mouths of submarine canyons, down at the base of the slope, that they infer to be sediment slides. But I don't think there's been a consistent effort to try and date them. But if they were Younger Dryas, then the very the interface between the slide layer and the overlying sediments should show some sort of distal impact ejecta. So there should be a peak in like these microparticles right at the interface between the slide layer and sediment deposited since the date of the slide.
so let's sort of, when we're talking about the microparticles, we're talking there, like for example, microspherules that probably solidified out of vapor. Are
Right.
we? Is that?
Yes,
And
and
then they show
also
this.
and I mean Alan West. I've been talking a lot to him, and what they find is they look and they see these microparticles, and very high in platinum group elements, which are also considered you know diagnostic of impact ejecta, and they see them in the Younger Dryas layer, and so they've been looking in the and the thing about it is if you have a big enough impact, and this Indian Ocean impact would have been one, and probably the one in North America, what's going to happen, and the water vapor is going to help the whole thing. I mean, I should say that I've also studied volcanic eruptions, and I've been recently fascinated by the eruption of Hunga Tonga because it was an underwater volcano, and the normal height of the eruption plume from a volcano is, like Pinatubo, which was the recent large eruption. So the eruption plume goes up 30, 35 kilometers. The eruption plume from Hunga Tonga, which was underwater, went up 658 kilometers into the mesosphere, where it triggered lots and lots of thunderstorms, and it was a relatively small underwater eruption. So, if you have a big impact, either into the ice sheet or into the ocean, the impact vapor plume isn't going to go up just 58 kilometers, because the height to which the plume rises is basically a function of the amount of heat that's injected. So the more heat, and water has a a tremendously higher heat capacity than air. So if you vaporize water, you're getting stuff that's going to go to the top of the atmosphere and into space.
Mm.
So I
Uh-huh.
think that these microparticles from the Younger Dryas could be all over the planet, because some of the oral traditions also talk about a time of darkness. And if you have enough material coming up from an impact and going into space, it's going to take a very, very long time to settle out, like years. And so you could have had a
Mm-hmm.
period. And some of the oral traditions sound like that's what happened. And then
Mm-hmm.
that stuff, it would have traveled. It would be all over the planet, basically.
And I've traveled a lot across the southern margin, from basically from the Pacific almost to the Atlantic Ocean, following the margin of the ice sheet and looking at the meltwater discharges. And obviously they vary quite a bit, but when you get out in the western, the Pacific Northwest, some of those discharges were extraordinarily huge. I mean, hundreds of millions of cubic feet per second, which is what I got to convert that to meters in my head. Roughly, if I say there's 300 million, and I divide that by 36, let's
Well,
see,
how
one,
many
two,
Great
three,
Lakes? Say how many,
30.
something like that. I mean,
Yeah. So
it,
yeah, one, two, three, one, two, three. So looks like eight. One, two, three, one, two, three. Looks like about 8 to 9 million cubic meters per second. Some of those flows, and yeah, Great Lakes. So Lake Missoula, which is probably the biggest of the proglacial lakes, that is blamed for the flooding, was was about 2,000 and some cubic kilometers. I always think, I still think in terms of the imperial system, miles and feet and all of that. So I have to convert, and that's why I keep this handy. But so 600 plus cubic miles of water puts it a little bit smaller, I think, than Lake Superior. And
wow, that's a huge amount of water.
that's a huge amount of water. And I don't know how much you've looked into that whole Channel Scabland flooding event.
Oh, I, I,
But
I went to a field trip there, and it was wonderful because when I was an undergrad, there was a guy who did experiments, flume experiments, and so he showed us both regular dunes and anti-dunes. Like if that you had a flat flow regime, and then you got dunes, and then you had another flat flow regime, and then if the velocity was great enough, you got anti-dunes, where the
mhm,
dunes were traveling upstream.
upstream,
Yeah.
yes. So, I mean, what is that implication? I mean, it's that, a huge volume of water, a lot of momentum, a lot of energy in that current, because some of those hills that it's literally overtopped. Not that the entire hill was submerged, but the wave itself. We can see there's a couple of anticlines there, in the it's called the Quincy Basin in central Washington, and you can actually see very clearly where a wave of water came from the north and washed up over the top of the anticlines, and in a couple of places it sort of downcut and created saddle-like features. And then you can see the sediment plume on the opposite side, the downcurrent side. So you can see pretty obvious that the water initially overtopped the rise that was formed by the anticline, and then so I have problems with the idea of an ice dam being the ultimate explanation for those
What,
floods,
an
and the
ice
reason,
dam, you said? Yeah,
yes, an
well,
ice dam.
the thing is, I was reading up on it because you were asking me about impacts into an ice sheet. And one of the things that they said is that an impact into an ice sheet could cause big calving events off the
Yes,
glacier. But
yes.
also, I mean, if you had something like an ice dam, if you were close enough, you could break the ice dam.
Oh, absolutely. I guess my problem is that where the ice dam was, and I've been through there probably 10 or 12 times, the water level behind the ice dam rose to 4,200 feet above sea level. Pretty consistent throughout that whole basin of the
Wow.
lake there. Now, on the other side of the ice dam, you're on the lee side of the ice dam, you're about 2,000 feet above sea level. So you've got an ice dam there that's that the bottom, the elevation of the floor of the valley where the reservoir is about 2,000 feet above sea level. The water was 4,200 feet above sea level, so that means it was ponding against ice over 2,000 feet deep. Now,
Wow.
to me, the more I've thought about that over the years, the more I think that's an impossibility. And the one thing that I did to try to get some framework for thinking about it was I started looking at modern glacial outburst floods, and there's been dozens and dozens of them documented. And they are absolutely minuscule compared to what this scenario would require. And typically 1 to 300 feet, it seems to be about the maximum depth of water against glacial ice, whereby the pressure of the water can either percolate directly through the ice, under the ice, or around the margins of the ice. And when you look at these examples of modern ice-dammed lakes that have broke through over the last 100 to 150 years, roughly, I mean, again, they're utterly minuscule compared to a hydraulic head that's 2,100 feet deep would create pressures on the toe of the ice dam, and you could convert this to
Yeah, but
alternative dimensions.
you're
But
talking
that
about
would,
Yokolops, right? Like the Yokolops
yes,
in Iceland. The
it would be
problem is,
like,
is it's kind of different because what's happening there is you've got a lot of heat from the volcano, and
right,
it's melting ice, and then what happens is it kind of the water builds up until it floats the ice, and then
right.
it all comes out. Now,
Tip,
if you're in
typically,
a
I think,
situation where the bedrock doesn't have a lot of heat, you could definitely get to the point where to get to the point where you float the ice, it has to have a much higher hydraulic head.
right. But, okay, part of the problem is not on bedrock. There's sediment. The valley floor is sediment, thick, and I don't know, I haven't seen well cores, but I know it's quite thick. And then you have a 1,100 foot deep basin, which is Lake Pend d'Oreille, which is right where the ice dam presumably was. So then my question is if that was water under there, and it's got to be a tempered glacier. I mean, an implication is that it's a tempered glacier because obviously you're not going to have 600 cubic miles of water next to
Right.
a frozen polar glacier. It's got to be a tempered glacier. Tempered glaciers ride on basal meltwater, and it's pretty much meltwater. I mean, this is what's at the bottom of a tempered glacier. So on the lee side, on the downcurrent side, below the ice, there was a documented volume of water that's called what do they call it? Not I've forgotten the name of it. Lake Columbia, right? And Lake Columbia filled up and occupied the channel that is now both the Spokane River, which is a tributary to the Columbia River, where it comes out of British Columbia and then turns to the west. And right there, the Spokane River meets it. And there was another body of water that would have been literally lapping at the toe of the ice dam that was 1,000 feet deep. Then on the upside of the ice dam, you had water 2,000 feet deep. And then under the ice dam, presuming it was tempered, I mean, all tempered glaciers have a pretty generous amount of meltwater at the bottom. So my thought is and given that what we see is that with pressures 100 to 200 psi, the water can actually start percolating through an interstitial cavity network that's in tempered glaciers. There's also fractures, tunnels and conduits, almost honeycombed. A lot of these are. So I just think, and we could certainly talk about this more, but I don't want to digress too much off because I want to get into your PowerPoint show here. But I think that there's room for some discussion here about the mechanism of some of these peak discharges. And I'd love to talk more with you about that.
Yeah, I think in some ways you probably need to talk to a seismologist about that because
Mhm.
if you had a big earthquake and or an impact into the ice sheet, which basically, if it's a big enough impact, it's equivalent to a magnitude 8 earthquake,
Yes,
then
yes,
then the seismic shaking would crack the ice, and
yes.
also it also could trigger induce seismicity,
Hmm.
which then you could get a flood as a result of that.
Well,
But
the
I
majority of geologists whose papers I've read or who I've been out in the field with maybe one exception, Jerome Lessman, are not looking at an impact at all as being in any way connected with these
Well, the thing is,
floods.
I've heard that now they think it's not just one big flood, that it's multiple events, but I don't know if that's right
Well,
or
see,
not.
then when you, because I think that the even one ice dam scenario of 2,000 feet depth water is problematic. It just multiplies the problem if you say, well, the ice dam failed and then resealed the outlet there at Lake Pend Oreille again and again and again. I just think when you start trying to make sense out of that, it just somehow doesn't add up. There's problems with it, particularly in the context of what's ice everywhere else doing. So the ice is in recession everywhere else, but in this one particular lobe, the Purcell Trench lobe, it seems to be completely regrowing. And you have a marginal profile of the ice, which means that if it's going to be, if the water's 2,100 feet deep at the water ice dam interface, the ice itself has to be at least another 10 or 15% thicker than that, right? Or it would become buoyant. So
Right.
the ice would have to be 2,400 feet, 2,500 feet thick right there. Okay, so if you have a flood discharging from there, and Victor Baker back in 1973 calculated peak discharge, and again, I think in terms of cubic feet, but it was about 7 to 800 million cubic feet. And he was the one who pointed out that that's more than 10 times the combined flow of every river on Earth. And that flow came down through Spokane Valley and then discharged out onto the Columbia Basalt Plateau, right there south of Spokane. But so he was the one who in 1973 proposed that came up and basically doubled the peak discharge that had been coming out of that the basins of Lake Missoula. And so I
Yeah,
don't
I
know.
think we're
At
getting
that
out
point
of
he
my
was not
field of
talking about
expertise.
multiple floods. Well,
No,
okay,
the initial
sorry,
thing was not
but
multiple floods.
to me the problem, and I'll sum it up very succinctly. If the water comes through at that rate of hundreds of millions of cubic feet per second, it's going to completely wash away the ice dam. There's going to, after the floodwaters are gone, the lake is drained. There's no ice dam there. Now the ice has to grow again. It has to move south, and it has to be at least, the snout of it has to be at least 30 miles or more from the point of contact with the water. In other words, if you look at the marginal profile of an ice sheet, to get half a mile thick, it has to be roughly 30 miles long because it's tapering down to nothing. So then my question is how fast is that ice moving? And you have to assume that the ice is moving and the water level is rising. Yet, as long as this 7 mile wide valley has any openings in it, the water continues to drain. It's not going to pool up and form a reservoir. So, in order to begin retaining the water to create the reservoir, the ice has to completely encroach upon that valley, which at 2,000 feet is 5 miles wide, at 4,200 feet is 7 miles wide. So, until there is a complete seal along that whole perimeter, that hydraulic perimeter there's going to be no way to retain water under the growing pressures. That's my problem with the whole thing.
Okay, well, I think you've highlighted some problems, but I think you can look at the scenario of what would happen if something struck the ice, because it certainly would melt a lot of water.
Yes, yes. That's where I'm going with it. Exactly there, Dallas, is that right? Rather than a slowly filling reservoir, and the models now allow 50 to 100 years to fill that reservoir, and for the dam to encroach upon the valley and seal it off, and to fill the reservoir, what they've done is they've taken the flow, the modern discharge rate of the Columbia River and no, I'm sorry, of the Clark Fork River, and doubled it. And then the idea is that if you roughly double it, you're going to have about 100 years or more, or 50 to 100 years within that range to get full pull at 4,200 feet above sea
Okay,
level.
well then, if it was an impact, then at the very top of that layer, there should be some of those microparticles.
Yes, but at this point, I don't know that anybody has actually looked for them. And if you don't look for something, you're not going to find it.
Yeah, well, that's that's one of my things is if you don't look, you don't find. So
Well,
yes. So anyway, somebody needs to look in a place where they think that contact is well preserved and see what they find.
and I think where that would be is in some of the back flooded areas, where just like with the tsunami, you've got the main trunk valley of flow, which is enormous, but then you've got tributary valleys, and as this augmented flow comes through the main valley, it also backfloods up the tributaries. So I've actually I can find places in tributaries where you can see the sediment deposit of this backwash, this backrush or backflood that extends up the tributaries, slows down, stops, and reverses current, and it'll leave a sediment pile there.
Yeah, I
And
think the
I
easiest
actually,
place to do it is to find a lake that where the water flowed into, because then you don't have to worry about erosion after the event. Just
so
find a lake.
there are many lakes within the path of the floodwaters.
So you find a
Mo-
lake, probably a distal deposit would be better, and just take some cores and see what you find. But the
mhm.
microparticles, you're not. I mean, from the stuff in the Hudson, I know now that the microparticles, we found them by using the eye tracks at Lamont, and you could see that there was this extraterrestrial signal, and then you do microparticle work afterwards. But it's not visible to the naked eye. You have to actually do some
Right.
chemistry.
Well, should we take a look at your very interesting presentation that I have here?
Yeah,
After all
I
the
don't know.
trouble we went to get it up on my computer here, we could. I'm
I
going to
think
get it
what
up
we're.
in presenter mode. Then I am
I
going
don't know
to.
which one we already talked about Madagascar quite a lot.
So we
Um,
can, yeah, we'll just start and we can skip over as we. Okay, we've talked about that. I'll jump to the next one,
yeah, the
and then as
first
soon
one
as
is the Gulf of Carpentaria event.
which would be associated perhaps with the 536
Yeah,
AD.
maybe with 536. It's within that time frame.
Uh-huh. So I talked with a gentleman today in El Salvador. They're having a conference down there. It's called, in Spanish, I forget, but it translates roughly as Layers of the Earth. And there's going to be some geologists there. There's going to be government representatives and a bunch of, there's been some major political and economic changes in El Salvador in the last 5 years. And they're one of the first countries now to accept Bitcoin as a medium of exchange. And so you've got like all these Bitcoin entrepreneurs that have made a bunch of money going to El Salvador, and they're wanting to ramp up their science. And this guy was primarily involved with archaeology. They're looking at a bunch of archaeological sites that have not ever been explored in El Salvador. But I talked to this gentleman today, young fellow, probably in his early to mid 30s, and he'd been out to the volcano that I think you've written about. It's huge volcanic eruption that was around 536.
Yeah, but we haven't figured out the source volcano, except I can tell you that it was underwater. There
the
are other,
536.
yeah, there are other people who propose that a volcano in Central America was the source of 536, but I have ice core data, and it shows that, and we found marine microfossils in the ice core at the 536 AD horizon, which indicates to me that it was an underwater eruption. And also that
Interesting. Well, so
eruption, which was originally proposed to be 536, has been redated.
okay,
It's not
been redated.
536.
Do we know the date? Well, but we do assume that something happened around 536. I mean,
Yes, and there's
the tree rings
it's
show it.
clear that yes, the tree rings support it. But I found cosmic dust in the ice core um, between
And
533 and 539, 540. So there
uh huh,
was increased cosmic dust entering the Earth's atmosphere at that time.
uh huh.
If and there and there was an underwater eruption around 535.
Interesting. So this sort of along the lines of Hunga Tonga Hunga eruption,
Yeah, and
perhaps, but
so the thing,
larger probably.
yeah, and then there was another eruption in 536. So I think the most likely scenario is that you had two fairly large eruptions close in time. And the thing is, if you look at Tambora, which was the most recent large volcanic eruption, that was in 18. Remember, it was 1815. It was in the spring of
Right.
1815 that
Yeah.
eruption happened. But then it was 1816 in the summer, 15 months
Yeah.
later at least, it was 1816 and froze to death. So if you have a large equatorial eruption, the climate effects are not, and it's in the right location and the right month of the year, the climate effects won't manifest themselves until the next year.
Until the next year, and that's what happened. A
So,
year without a summer.
so what
We're
I
talking
think,
about.
and I mean the descriptions, the historical descriptions of 536, it sounds like there was a volcanic eruption that obscured the sky. So there
Hmm.
was something, and actually I have ash in the ice core at both 535 and 536. And so I think there was both, that there was an eruption in 535 and then a tropical eruption in 535 undersea. And then there was later uh, an eruption from a volcano, I don't, probably not tropical, but sort of mid latitude. And so
Uh huh.
it was like a double whammy. You had two large eruptions close to each other in time. So I
So
think that's
then,
why it was so bad.
so what
But
was the dating then of the Gulf of Carpentaria? Is
we know it's within the last couple thousand years, but we don't have a good
okay.
date. And the reason why we
Can't
don't,
pinpoint it and
yeah, that
associate it with the 536 AD event,
it could be,
is what you're saying.
but
Could be, yes. It's within that window, but you can't exclusively attribute it
right.
to
Part of the
that date.
problem is that if you
Okay.
have a submarine impact and and you're you're excavating the pre-existing basement and the pre-existing sediment. And so what we
Hmm.
found when we tried to like narrow down the date, we have this layer that we think it's got spheral aggregates and we think it's an ejecta layer from the event. But the thing is, what we
Hmm.
got was we got we got above the layer we had young dates, below the layer we had fairly young dates, but somewhat older. And then in the layer, when we carbon 14 dated, we had dates that were older than either above or below. And so it made it, and that makes perfect sense because if you have an, a large impact crater forming, you're going to be excavating all this old sediment.
Hmm. Yeah. Okay. Yeah.
And so that, and we were too close, basically. You need to be further away where the ejecta layer would be thinner, and then you would have some hope
Thinner.
of getting a good date.
Right. And you could run into the same problem trying to date flood sediments because the floods are going to entrain older sediment. So
Right.
if
That's why
you're,
I think you need to
you know,
be at a distal site
uh-huh. Yeah. So if a
because
flood came in
because
and washed some organic material up at the time of the flood, but mingled with that is older material that was already part of the soil or part of whatever the
right. But the
substrate was
thing is,
composed of.
the date of the stuff on top of the flood layer, that
Hmm.
should tell you the age. And
Right.
particularly if it has those microparticles, like a date just
Hmm.
right where the microparticles themselves are probably not going to have any organics with them. So you
right.
date right at the microparticle horizon or slightly above it. That would give you
Hmm.
the age.
Okay. Well, let's see. Let's do this. I will do a share screen here, and we will dive into wow. Okay.
Yeah, so
So
I
this
talked about the Gulf of Carpentaria,
okay. So
which
we can
is,
just start scrolling through, and you tell
yeah,
me.
keep,
I'll you want to
so,
go through this?
so the, yeah, so you keep going.
Okay.
I mean, so this is the Gulf of Carpentaria and the crater candidates in the Arafura Sea. And basically, the crater candidate in this case was found using gravity gradients, but we looked at cores in the Gulf of Carpentaria, and we found these really odd things called spheral aggregates. And
Pseudo aggregates?
spheral aggregates.
Oh,
You
spheral,
move,
spheral.
you can.
Wha-
I have a picture, but it's further on in the
Okay.
presentation of what they look
Well,
like.
just orient people. This would be the northern coast of Australia here, I'm
That's
guessing, and
right, and that's
this
Papua
is
New
New
Guinea.
Guinea. Yeah.
And
Okay.
also in Papua New Guinea, there are some oral traditions of hot water coming from the sky.
Aha. Okay.
So,
And so that
and there
sort of
was
fits,
also
doesn't it?
in the Gulf of Carpentaria on the western tip of land, right above maybe the
Mm-hmm.
F in Gulf, there was a tradition
And
of rainbow
oh, right
serpent
there.
coming in and eating up all the children. And one way to
Oh,
interpret
really?
that is that there was a tsunami.
Okay. Eating up the children. That
Yep.
wasn't nice.
No.
Not nice at all. Okay.
So this is
We
a
got
gravity gradient map, and the crater candidate's at the very top there, and it's about 40 kilometers in diameter.
mm-hmm.
And then these are the
Oh,
cores where we found spherules and spheral aggregates.
uh-huh.
All these,
Okay. All of
and a
these.
few of them we
All
also
right.
found native iron, which is also another thing that you can get in an impact. I mean, basically, the spherules that form in an impact, they, if like if you just had they're mostly made of iron oxide, but the iron oxide is very depleted in oxygen compared to the iron oxide that you'd find just lying around on the ground,
Mm-hmm.
because impacts are very reducing. They produce very reducing conditions, so you basically
Uh-huh.
you don't have that much oxygen.
Okay.
I
Well,
mean,
that would
really
account
big
for it, wouldn't
impacts, you may actually remove the Earth's atmosphere right over the site temporarily, of course.
it? Yeah. And that would create the reducing conditions.
Yeah,
Am I right? Yeah.
yeah,
And so these with the black squares in them, is your where you've got native iron, as you
that's
say.
right.
And then, what did you just? Oh, you got tektite shaped spherules with quench
Yeah,
texture. So the quench texture is the surface, the mottled kind of look of the surface, and that's the result of fast uh, hardening, crystallizing. Is that correct?
that's because it crystallized very quickly. I mean, you could somebody
Yeah.
who's welding, and then the little bits of iron from the welding,
Mm-hmm.
if they're just like they're put into a vat of water, you get the same thing because you're
Uh huh. Uh
basically
huh.
solidifying something that was very hot very quickly. That's why it's called a quench texture. Because if you were
So you've
welding,
got
you would be quenching the iron.
yeah. Okay. So you've got cores containing magnetic tektite shaped spherules with quench textures.
That's right.
That's pretty unambiguously an indication of some kind of a high temperature, high energy event, right? You can't get around
Yeah,
it.
yeah, I think
Okay.
so. I mean, and they don't look like cosmic spheres, which you can also get. But the thing
Right.
is, the
But
spheral aggregates, they've produced those experimentally from extensive lightning. Actually, the
mm-hmm.
person who's been doing the work has been working with volcanic ash. But you can also, I think, but hers are mostly silicate spherules, and ours the ones from impacts are mostly iron oxide spherules, and also
Now,
hers are small spherules, and ours are much larger.
is
So
that D? One of your co-authors, D.
no, this was I'm trying to think of her name. I think she's in Alabama,
D.
University of.
Brager?
No, Dee Brager was the microscopist that I worked with.
Microscope. Okay, yeah, that's
Yeah,
okay.
she was amazing.
I
Really,
bet.
really took amazing pictures
Uh-huh.
on the SEM.
Wow. And just for the listeners, SEM is your scanning electron microscope.
That's right.
All right, let's go to the next slide then.
So
Okay.
here's the crater candidate, and Walter H.F. Smith modeled it. So basically, he's got a sediment-filled crater with dense rocks near its center. Would produce he can basically reproduce the gravity anomaly, but he puts
Okay.
a dense rock in the center, but actually a crater that size would have a central uplift. So I think if he put a
Uh-huh.
central uplift in, it would reproduce the data also.
Right. Okay. So I see the gravity anomaly profile is going to be, and is that going to be an indication of that the bottom of the crater is probably going to be brecciated, correct? It's going to
Oh,
be broken,
absolutely.
and
Yeah,
that is going to affect the gravity profile, right? That you
right.
can actually,
I mean, if we could get a seismic line over it, we would know immediately that it was an impact crater, because whether or not it was an impact crater, because the basement, the rock underneath it will be brecciated, and you can see that seismically.
yeah.
And I also think
And
it's very likely that you would see a central uplift, because the really
right.
large craters have a little hill in the middle.
Yep.
It's called a central uplift.
There is a crater called Middlesboro Crater. It's right up on the Tennessee-Kentucky border, and it's famous. The citizens of Middlesboro are proud of the fact that they're supposedly the only town in America that's built inside of an impact crater. And it's about 6 miles in diameter, the crater itself, and it's quite old, so it's also eroded down, but there's a central uplift. And I've found some logging roads. We were able to get up on the rim, so you could look down into the whole circular basin. And once you get up there on the rim, it's pretty, you can definitely see the circular outline of the ring of mountains. And then right in the middle, right where the uplift is, they've built a golf course on top of the uplift. And I was wondering, as I was looking at that, I wonder how many of these golfers really understand that they're playing golf on this central uplift from this ancient catastrophic impact. Probably not very many of them, but
I'm
I
sure
bet there's
not
a
very
few of
many
them.
of them.
But yeah, yeah, but yeah, so there's a golf course there. And they have a museum there in town about it. But the day that I was going through town there, the museum was closed, so I didn't get to go in there and see what they had there. But we did find. I asked a local cop. I said, you know what? I said, this is a impact basin that we're in. He knew. He didn't know much about it, but he knew. And I said, well, I want to get up on. We're trying to get up on the rim so we can get a view of it. He says, oh well, and he told us right where to go, which was nice, because sometimes you're out in these areas and you're like, hey, is it against the law for me to be here right now? Am I going to end up in jail today because I'm trespassing or whatever? But yeah, you could see very clearly, and it was impressive. I mean, have you been to Meteor Crater in Arizona?
I have not.
Okay,
We
okay. I'm going to
voted
get
in the
you on our
Petrified
next
Forest
tour,
one.
Dallas. Would you, if with all expenses paid on a tour, would you come along and maybe agree to like give a couple of lectures over 3 or 4 days? If
Yeah, I would go to Meteor
I
Crater,
take,
sure.
yeah, I've taken people, I think 4 or 5 times there to Meteor Crater. Most of them who've never been there. But you stand on, it's a baby. But let me tell you, when you're standing on that rim and you're looking, it's a kilometer across and 600 feet deep. It's one hell of an impressive hole in the ground. And you're thinking to yourself, my gosh, this would have been, I mean, the eject of it, there's a study that showed the ejecta was I forget, many miles away from the crater itself. And you can actually, especially when you're up on the rim of the crater, you can look out over the desert floor and you can see, they don't let you pick it anymore, but you can see, remains of the ejecta, scattered over the desert floor. It's very impressive. And then when you realize, okay, this is at the very bottom, the very small end of the spectrum of impact energies. And then, like you've probably heard of Cumberland Gap, where Daniel Boone took the settlers when they were trying to cross the southern Appalachians there in
Uh-huh.
Kentucky. And there was the Cumberland Gap. So it's quite well known historically. But that gap is actually an open fault line that's in the rim of the Middlesboro crater.
Oh, that's
I'm
really
guessing when
interesting.
Daniel Boone led the settlers through that fault line there, through that open fissure in the rim, I'm thinking he was not thinking, oh, we're walking into an ancient impact site here. That probably did not cross his mind. But it's very impressive when you're up on the rim and you're looking at this thing and it's over 5 miles in diameter. It's very impressive.
Yeah, well, there's a lot of places I'd like to visit for sure.
Yeah, me
So I get,
too. So
we're
I'm
kind of,
taking some. Pardon me.
I think we're getting, it's been going, we've been going for an hour. Do you think we
How
should,
much longer do you want to go? I'm good for 20 more minutes, 30
well,
or 10 more minutes, whatever you're good for.
I think 10 more minutes would be good because
Okay, sure. Well, then let's go ahead and get through some of this here.
yeah, so this is the stratospheric lightning that produces the spheral aggregates, and it can do it either
Mm,
during oceanic impacts and also during volcanic eruptions like Hunga Tonga.
aha,
I
large
mean, Hunga
stratosphere.
Tonga, when it was erupting, at some points there was stratospheric lightning. It was the biggest source of lightning on the entire planet.
Oh, wow. I did not know that.
Yeah,
Okay, produces large.
so here's the spheral aggregates, and
Look at
this
this.
yeah, so you can see these round metal spherules, and they have the quench textures, these beautiful quench textures. And the thing is, this thing is only 2 to 3 centimeters down in the core, and it's surrounded by
Oh,
completely unlithified sediment. And so
so it's very young.
yeah, it's geologically very young, and and it's far enough from shore. It's not like something that could have just gotten washed off from land. In fact,
Aha.
if it was, I mean, it couldn't have been in a river because look at how that stuff is like just sticking up. It would
Yeah,
get eroded off in a river.
yeah.
It's got very angular fragments, and so this is something that basically it probably came in a tsunami wave, but it could not have come in by fluvial transport, and it could not
Okay,
have been eroded off the land.
right. And it's probably less than a couple of thousand years old.
Right. It's definitely, I would say it's definitely less than 2000.
Okay. That's I mean that's amazing. I mean
Yeah,
that's
they make these mostly, a lot of them are perfectly round, but some of them are tektite shapes.
yeah.
And see, here's a
Oops.
cross section of the same one. Of the
This one here.
same, so this is the same one that I just showed you the
Okay.
picture. And you
So
can
this
see
is
the
yeah.
spherules. You can see
Yeah.
that some of them are hollow. One of them was not perfectly round, the one on the left, but there were these iron spherules.
This right here.
And then the ones that they've made experimentally that form during volcanic eruptions, the largest ones are 80 micrometers in diameter. And see the scale bar? These
Yep.
things are larger. And the one on the bottom right is like over
This.
200 micrometers in diameter. It's just a piece of one.
A piece of
So,
one. So
so, so
it
these things are way too big to have formed from volcanism, and also these things are iron oxide, and most of the materials that form from volcanic lightning are silicate.
aha. Yeah. Interesting. Okay.
And so here's a map, because of course what people were trying to the bottom right with the blue thing,
Down here.
that's a nickel element map. So it shows that that thing has some nickel in it, which
I
is a
see.
marker for extraterrestrial material.
Sure.
And then on the left, we've got maps of the green is oxygen and aluminum,
Mm-hmm.
and the red is iron, and the blue is silicon in the upper left. And
Right.
the point of that is that there's not one of the things that people look for in impacts is they look for shock quartz, but most of the little rock fragments in this thing, they're not the iron, but the rock fragments are actually feldspar. So
Mm-hmm.
it's very hard to find chalk quartz in these samples because they seem to be dominated by feldspar.
So you don't get those same PDF formations in feldspar that you do in quartz, or you
No, what
do?
happens
You
with
don't.
feldspar is it turns into a glass, but it's
Okay.
called mescalinite, but it's not
Ah.
considered diagnostic of
Okay.
impact. They
Aha.
want the shock quartz, but what we're going to do is look at this thin section some more and try to magnify it and use and see if we can find some some localized pieces of high nickel
Mm-hmm.
because it looks like there is nickel there, but we just haven't. I mean, if you look enough, I think we would actually find impactor pieces.
So where was these sediments just found?
This was in one of those cores that we had on the map,
From the
and
bottom of the
above
ocean
the
there?
Gulf of Carpentaria.
Okay, okay.
It's
So it was a
but
sea
it's
bottom
several
core.
kilometers away from the crater candidate. I think it's a tsunami deposit.
Okay. And then this was found pretty much almost right at the top of the core.
Yes.
Aha.
So it's geologically extremely young.
Okay.
And this is just showing the largest fragments.
Okay.
And for some reason, the largest fragments are, they don't increase in size necessarily towards the crater candidate. I think there may be some optimum distance where you get the big, you get the biggest tsunami waves.
Aha.
But, these things are, and those were the mean, but we also see the ones where with the smaller fragments, the mean water depth is slightly smaller. And you get more
As you're
friction with the tsunami wave if the water depth is shallower. So that might be part of the story.
okay.
I think we do. And these are just showing models. The spherals make it more magnetic. So
Right.
that's the number of spherals, and then the pink is the magnetic susceptibility. And then the pink bar on the top is the thickness of an ejecta layer from a 35-kilometer crater. And the thickness of the layer with high magnetic susceptibility and spherals about matches.
Mm-hmm. Yeah, you see that right here.
Yeah.
So
So,
clearly something happened here.
right.
And the consequences are you had these magnetic spherals, enormous numbers of them, undoubtedly in the billions and billions
Right.
of
I
these
mean, the ones that
spherals.
we found, we found hundreds of them, but we were only looking at the largest size fractions.
Aha, aha, I see. Okay. So when you say magnetic susceptibility, is that because of the concentration of these materials, like iron materials and
Right.
nickel?
Iron, and particularly iron oxide, magnetite,
Aha,
is
okay.
it has a magnetic susceptibility that's like 30,000 times higher than most other minerals, like
Aha,
like quartz and feldspar, the
sure.
typical. So
Okay.
it's enormously effective at producing high magnetic susceptibility.
Aha. And over here, this is, let's see, the vertical scale on the left is the depth.
Number of spherals
Oh, number of spherules, I see it there. And over here, the
is
vertical scale on
magnetic
the right is the
susceptibility.
measure. Got it. Okay. And okay, and your depth is the x-axis
Depths the
down here.
bottom in the
Got it.
core.
Yeah. Okay.
And then the predicted thickness of the ejecta layer. So now we're back at the Indian Ocean. We already talked about the
Okay.
Chevron,
Kind of.
and there's the
We
Burkle
did,
Crater
but
candidate.
right there. Yeah. There it
And there's
is.
chevrons in Australia as well, southern Australia. So, and I
Right.
think they could
Oh,
both have formed from the been the
the
result of the
same event.
Burkle.
Uh-huh.
Okay, and
Oh
this
yeah.
is the
So there's
picture from the Teletot and Sheffer's paper, which shows the chevrons there. They're not so visible in Google Earth right now, but they did a
Yeah,
geological
because
map.
I actually have some screenshots from years ago where they're much more visible. I was able to find them very easily.
Oh,
So I'm not sure
really?
what's going on there. Yeah,
Well, I think if
yeah,
people are living in the area and they're farming it, that would destroy it,
sure, that could
or
be it.
just climate change. Because I mean, the ones that
Hmm.
are in Madagascar, one reason why they're so well preserved in southern Madagascar is very dry there.
Hmm.
So if you have any kind of rainfall, uh, or just there's all kinds of things that could be disturbing them.
Yeah, because just here this evening when I was scanning the coast there trying to find them, they weren't obvious, but the screenshots that I took, I mean, I could find them instantly.
Oh, that's really
They're on.
interesting.
Yeah, I could dig those up and send them to you.
Oh, that would be great. Yeah, because
Of
at some
course.
point I would like to go if I can get it out in the field there, and I can get the problem is to get permission from Aboriginal owners. Um,
Uh huh.
and then we could take samples.
Uh huh.
In
All right.
Madagascar, it was simpler. So this is what I was talking about with latitude. See, this was
Yeah.
the circle on
Yep.
the right. That's the proposed location. But the important
Okay.
thing is that it's got the same latitude as Burkle. And
I
and
see.
the
Yes.
and the chevron orientations don't they really they tell you the direction. They don't tell you how far away the source is.
Right. And what have we got going? Oh, another land under.
That's an undersea volcano, but it's not really at the right location. It's
Okay.
too far north to explain the
The mad.
directions of the chevrons in Madagascar.
Right. They definitely look like they were coming from this direction, from the
Right, yeah.
southeast. Okay.
And so there's the Burckle Crater candidate, and just some
E-
cores with basalt fragments. And one of those, we did find stuff. We found spherules and what looks like melted impact glass. We
yeah, there's
just
melted nickel right there. You
that,
found
that's
that.
another one where we found melted nickel. But the most recent stuff is like north of the Burckle Crater candidate, roughly north, but along the ridge, because
Oh,
it's shallower. So that if you have shallower water, it's going to slow the tsunami down.
oh, yeah. Okay.
And these are from the Southwest Indian Ocean that somebody else found.
Oh,
And it's got wustite, which is very characteristic.
I
So
was going
these
to
are
ask you about that. I
cosmic spherules.
okay.
And the wustite is basically if you have magnetite, and then you have something that's more reducing, you have less oxygen than its wustite.
Then
So
it's
it's
less.
iron
Okay.
oxide, but it's got much less oxygen than magnet or less oxygen than magnetite.
Uh huh.
And wustite is very characteristic of extraterrestrial iron.
Extraterrestrial iron. Okay.
Yeah.
Well, we'll
And
just go a
so
couple
here's what
more.
this new place, and we found spheral aggregates. So that it's a visible light picture on the right, and see that
Yep.
kind of brown thing, and then on the left is an SEM image, so you can see
Hmm.
the quench texture.
Yeah. Yeah, and that's what
Greater.
this.
I said here it's greater than 1 meter thick. We now know it's greater than 2.8 meters thick. We have collected data since the conference.
Uh huh.
It's
And
really thick.
what is the matrix here in which this spheral is embedded?
Uh, well,
Is that
it's
of any relevance?
probably solidified mud, ocean mud. We don't know
Okay.
exactly. It's just some kind of solidified material that
Okay. All right.
and this is the impact glass, which I love. On the upper left is a visible light picture,
Yeah.
and on the
Aha.
right is a picture of it that we just took uh, last
So
Tuesday.
these are almost like flow forms that were in the
Yes,
glass when
and
it
that's
was like in
what
a
you see
molten
in
state.
impact glass is that
Wow.
kind of flow texture. And you can see that it's got, and also on the bottom, what you can see is that it's hard to see in this image, but it's actually microvesicular. and the
Yeah,
vesicularity is
I can
very,
see
very
it on my
uniform.
yeah.
And Alan West
Right.
told
So
me he
that would be
sees,
from what, gas escaping from the molten?
yeah. And the thing is, the
What
microvesicularity
what did
indicates
Alan
that
tell you?
he said that he sees that kind of stuff all the time in his impacts in his stuff from the Younger
Uh-huh.
Dryas, and it's only close to the source. You only find it close to the source.
Uh-huh.
And we found a whole lot of this in this core. I mean, at the very bottom of the core, one of the layers we sieved like a 10 centimeter interval, and there must be 100 pieces of this stuff. There's a lot,
No kidding.
and
Well,
then
that's pretty strong evidence, doesn't it?
yeah, it doesn't all
Okay.
this one, and they'll go back to the back one, that spheral, the that
This
spheral on the
down
bottom
here.
left. Notice also it's
Yeah.
huge. It's like was it 400 or 600? I can't read it. Scale bar.
Yeah,
It's hundreds
600.
of microns across, and um, and it's not the same composition as cosmic spirals. So
It's not.
I
Oh,
think
yeah,
it's a
I see.
compact spiral.
Let's clarify. When you talk about cosmic spherules, we're talking about the slow, steady rain of cosmic materials that
Right,
kind of filters through the atmosphere on a daily basis, but no one could actually observe. It's pretty much uniformly dispersed throughout the sedimentary
right, and
column.
sometimes, but that's right, and sometimes
I
you get
think I've read that
these.
it's sometimes you get what?
Sometimes you get these bigger. I mean, for me, this thing, I mean,
Oh,
it is big, right? I mean, on the scale, on a
yeah,
cosmic scale. I mean, if you were to actually see it on a piece of paper, it would be like a little pinhead. But
of course. But looking at it through a microscope. Now, am
yeah,
I right that I'm not seeing any quench texture here?
it does have a quench texture. We just have to enlarge it
It
a
does.
little bit.
I got to look close. Okay, yeah. Now that I'm looking closer, I can actually kind of.
Yeah.
So how do you how do you tell the difference then between the the steady rain of cosmic spherules from something that produced a microspheral in an impact?
Well, it's composition. Like we're
Just
actually
its
going to make thin
composition.
sections of these things to see what the interiors look like, because that would be more
Uh huh.
diagnostic. But the other thing is, I can tell you that certainly the stony spherules, these have very low magnesium contents, and
Okay.
they're too low to be a stony cosmic spheral. But they also
Okay.
don't look like they have what they call the I-type cosmic spherules, which are very rich in iron, and they don't look like those either.
Okay. All right. Well, I wanted
And
to
then
see this because this.
this was one. It's basically this grain has pure nickel on it, and the melting temperature is greater than 1,500 degrees centigrade. So I mean, I think it probably melted during an impact.
Yeah, yeah. Now, when you say the nickel oxide drops, that's these things.
Yeah, those things.
Those things. Huh.
Yep,
Was this a scanning electron microscope image?
that's right.
Uh
Because
huh.
the 2 micrometers. Yeah, D. Brager
Right.
took that picture,
Oh,
and
okay.
yeah,
Wow. Okay.
and so
Well, I'm.
this is what
Yeah.
this is the Burckle Crater candidate, the new one. I had an old location, but we actually have a seismic line now. And the
Oh.
important thing is in this picture, you can see like the basement on the bottom one is
Mm-hmm.
the rock is sort of the black stuff.
Uh huh.
And then
Okay.
on top of it, in the hot in the lows, you can see what we would call an acoustically transparent layer. That's in the bottom profile,
Down
which is the
here. Yeah.
seismic profile. And
Yeah.
notice on that the one that I'm pointing to, the top of it's flat, and on the left, it's all goes up and down. And the thing is, if you have an impact, a large impact, what's going to happen is, first of all, there's going to be lots of seismic shaking, and it'll
Yep.
shake all the sediments off the hills. But it'll
That.
also
Mm-hmm.
fluidize the sediment, and then it'll make a flat layer.
Mm-hmm.
So that's
Okay.
why I think that one on the right, and also it will also fracture the basement. And if you look at the very below the black layer, you can see that below that hollow, the basement
Right
looks.
there. Uh-huh.
And then I've projected in the top one, I've showed where the seismic line goes, and that red line is that area of flat sediment.
I see. So
And you can
this
see
looks
that,
like a more likely candidate
right,
for the
because
impact
it's
site.
kind of it looks sort of circular, and I know this area isn't completely mapped, that
Uh-huh.
well. But the seismic line, I think, and so that's what I think is
Yeah.
now the candidate for Burkle.
And it looks like it's pretty close to the old location, so the back azimuth lineup is going to still be consistent.
Oh yeah, oh yeah.
Yeah.
But I
Okay.
would love for somebody to go in there and do some and with a seismic ship and actually
Uh-huh.
see what's there. Because this is a
Okay.
very old seismic line, and it's an analog seismic line, and with a digital seismic line, you could get a much better image.
Uh-huh. Okay.
And I also calculated from that location, with the deep water wave height, you could get a wave height of up to 82 meters. So the tsunami wave height is going to decrease less if the water's deep.
Mm-hmm.
And so you could get a tsunami with a wave height of what we saw in Madagascar, which was over 60 meters high
Okay.
from a crater at that location.
Okay. And this would represent the new location,
That's right.
which at this scale is almost the old location, but
Yeah. I mean, at this scale, you can't tell the difference.
right, right. Okay, but now you can see if the wave is moving out this way and then it refracts around the coastline here. I mean, it looks to me like that's exactly what would line up those chevrons, what we
Exactly.
see there. Yeah. Okay, and there's
Okay.
a
And then,
distinguished group of people.
yeah, those are two drivers on the left. And
Oh,
then
these fellas.
yeah, they needed to be bilingual in French and English.
Aha.
And then we had two Malagasy seismology grad students on the right. They both have
These two.
PhDs now in
Oh, okay.
seismology, but they were trilingual because they spoke English, French,
No
and
kidding.
Malagasy.
Wow.
They
And
were
who are
our
these two
interpreters.
gentlemen?
Okay, so the guy on the tall guy on the right is Slava, the Russian tsunami modeler. He also liked to go in the
Okay.
field a lot. And then
Aha.
the guy in the middle with the blue shirt is Ted Bryant, who
Oh,
is the guy who wrote the book on
yeah.
tsunami, the underrated hazard. And
Yes.
he was, I mean, I didn't know that much about tsunami, so he was our tsunami expert because he had worked actually with sediments,
Okay.
tsunami sediments. So that was our field group.
Okay. Well, do you think that that's a good place to leave off, or
I think so, yeah, because it's we've already talked for an hour and a half, and it's
sure? I
been a
think
great
that's what we.
pleasure. But I think it's time to.
Yeah, I agree. I agree. And I want to just one last thing, kind of wrapping up here. I mean, I look at this, not only from the scientific standpoint. I try to look at it more like also from like the social standpoint and the historical standpoint. And I'm always looking for, okay, what is, as we learn about these events in the past and how dynamic this planet is that we inhabit, and we now know, I mean, this is stuff that nobody knew 50, 75 years ago when both you and I came into this world. I mean, this is completely unprecedented knowledge compared to like when I was born in 51, right? But
Mhm.
what interests me is what are the implications? I mean, is there more to this than just an academic study? Interesting in its own right, profoundly interesting. But is there more implications for us considering going forward and what we now know, perhaps about cataclysmic events that perhaps pulled the plug on other ancient civilizations? This is kind of the perspective I kind of like to bring to these discussions. If you had just like a 1 or 2 minute thought on
Yeah.
that
Well,
before
I
we
think
go?
that basically, I mean, the reason why I ended up in going to Madagascar was because other people had gone there to investigate the Boxing Day tsunami. which
Mm-hmm.
killed quite a few people in Indonesia and propagated all the way
Yeah.
across the Indian Ocean to Madagascar. And the big problem was that they didn't, the big tsunamis are rare in the Indian Ocean compared to the Pacific.
Mm-hmm.
And they didn't have a system set up where they could contact people and tell them to get out of the way. And so I think, systems of
Right.
emergency preparedness, and of course the recent disaster in Texas where they had fired the guy at NOAA who was supposed to supervise, organizing people for emergency preparedness for things like that flood. They
Mm-hmm. Mm-hmm.
That kind of stuff is needed, and the thing is, you have to set it
Mm-hmm.
up beforehand. It's too late when the
Yeah.
event is happening.
Right. Once the rains start falling and stuff, it's too late. Right. So that's interesting. All right. Because that's what I'm always looking for. I mean, what are the practical applications of this knowledge as far as like going forward as a civilization?
But there are ways now. I mean, almost everybody has a cell phone, and like in
Right.
California, they have a system set up where people can get warnings for big earthquakes on their cell phones. So it's
Okay.
it's it's possible for people to be warned in time, but you just have to set it up, and people have to be willing to listen.
I think this was in one of your papers that you co-authored. I'm not 100% sure, but the and I'll make this short. The fundamental idea was that a lot of the traditional knowledge that has been lost, people knew and understood things like tsunamis, and maybe they'd experienced it. They knew that, for example, if you saw the recession, the regression of the ocean water, that it was going to be followed by a big wave coming back in. But when you see the videos of I guess it was 2006, you've got the people they're standing there gawking at the ocean bottom that is being exposed, and no one is realizing what that implies. And so there was
Exactly.
over 200,000 people lost their lives. And almost the comment was that, well, once upon a time, the people standing there seeing that would have known from their own traditional knowledge that had been handed down as a legacy what that meant. But to me, it was kind of like this signals that, yeah, a lot of this is being lost. Now we've got the technological means to remedy that, like you were just saying. I mean, with cell phones, that's pretty amazing. But it's interesting that when I'm seeing these videos of, there's people out on the beach and they don't know, they don't understand what the implications are of what they're seeing. Yet, probably if you went back 1,000 years ago and indigenous people are standing there on the beach seeing the regression of the water, they would have known what that meant.
Yeah, and I heard that there were people who survived the 2006 Boxing Day tsunami. There were people who had preserved their traditional knowledge, and
Aha.
they ran away and they
They
survived.
ran away
So,
and they
yes.
survived.
And also, in Japan, there was a very large, the
Yeah.
Fukushima earthquake, which ruptured.
Right.
Apparently, they had markers there in Japan of what the tsunami, run up had been, how far inland and above sea level it had gone in a previous large earthquake. And yet they allowed people to build a nuclear power plant in houses below
Yeah.
the elevation of those markers. So
Aha.
people don't like being told, "Oh, you can't build here because it's dangerous." And
Right.
and
I'm going
so,
to stop share.
that's a problem too.
Yeah. Well, this has been very interesting. I've learned a lot, and I hope maybe sometime in the near future, not too distant, we could do this again because there's a whole lot more things I'd love to talk to about, and I'm sure you had more things we could get into. But
Yeah,
we're probably
and now
both
that,
tired. It's been a long week, but I can't tell you how much I appreciate you having this
well, thanks. And
conversation with
and
me.
I and I thought your what you had to say about the floods was interesting. So,
Well, I'd like to show you, and I'll, at some point, in the next few days or whatever, I'll send you some screenshots so where you can see where there are land-based chevrons out in eastern Washington on the Columbia Basalt Plateau. I mean, they're almost indistinguishable from what we were just looking at.
Oh, that's
But it
interesting.
was, yeah, I mean, it was major water flows, and it was a bidirectional. So the wave first flowed to the west. There was a 200-foot ridge called the Babcock Ridge. We can see two spillways where the water topped over the ridge and dropped about 800 feet, stepped down into the Columbia River channel, and then the water back surged because it washed up. It came from the east, washed up on the ridge, overtopped the ridge, filled the basin with water up to about 400 feet deep, and then the water drained back off in the opposite direction. And there's a massive field of chevrons there, and they look very much like the tsunami deposited chevrons. And I remember somebody, a critic, attacking your idea when it first came out and said, well, we know that these are windblown because there are chevrons on the land. So I looked up to see what example of chevrons on land are you talking about, and one of them was the chevrons in Washington State. And my first response was, and I'd been out there already numerous times, I said, well, they're deposited by water, huge volumes of water.
That's really interesting.
Yeah, 100 plus million cubic feet of water surged into this Quincy Basin meltwater and then flowed back out again. And I won't take your time now, but maybe that would be an enticement that you and I could have another conversation in a not too distant future.
And also
but I'm going to do some
deposit
screenshots and send them over to you so you can deposit where?
well, there's also the tsunami deposit in the Hudson.
Let's
So
see.
when we know more about that.
Oh, in the Hudson, yeah. And I've got an invitation this fall. I've got some friends that have they have restored an old resort up there in the Berkshire Hills overlooking the Hudson. And I've gotten up and I've studied the Finger Lakes. I think the Finger Lakes are worth looking into, and that's something I'd like to converse with you about in the future.
Okay.
You know, they're huge, deep troughs, and they're half filled with sediment. And the studies from maybe 15, 20 years ago when they first took core samples from the sediment filling the Finger Lakes, one of the surprising things was the oldest date of the sediment. First of all, it was two layers. They figured there was going to be annual varves, but they didn't find that. What they found was two massive layers of sediment, and the oldest radiocarbon dating kept up coming consistently at between 14 and 15,000 years old. Very interesting. And I think that they were probably created catastrophically, very much like Grand Coulee out in eastern Washington.
Oh, that's a
And
really interesting idea. Certainly worth looking into.
yeah, well, so I'm gonna try to pique your interest in a little of this that I've been looking into, because I'd certainly value your impressions and opinions about some of this that I'm constantly turning in my head. But anyways, I'm going to start by sending you the screenshots of these chevrons in Columbia Plateau of eastern Washington and see what you make of them. So on that,
I'll
you
be
got
at the
anything planned for
ATU.
the future?
Yeah, I'm
What?
gonna be. I'm writing an abstract for the American Geophysical Union meeting in New Orleans. It's in December.
Oh, okay. Okay. Good to know. All right.
Yeah.
Well, I'm going to sign off then, Dr. Abbott, and thanks again.
Okay. Well,
So
thank you, Randall. So good
you're
night.
welcome. Good night.